Hello there folks, how you doing? This is Mike coming back at you with another video on Foundations of Math 2. In the previous video we introduced some formulas pertaining to regression analysis. We talked about the correlation coefficient between two quantities x and y and the linear regression line, or the best fit line. And we saw these ugly, complicated formulas that we have to use to figure out what those things are. In this video, we're actually going to go through some sample problems here, and we are going to see how we use those formulas to solve some particular sample problems. So you'll be given some data points, some ordered pairs, and you'll have to find the correlation coefficient. You'll have to see if there is a large enough correlation coefficient to give us reason to think that there is a linear relationship between the two quantities, and then you'll have to find the A and B values that you have in your best fit line, or in your regression line. So let's get right into our first sample problem here. Given the ordered pairs 1, 3, 2, 5, 3, 9, and 4, 6, determine the correlation coefficient R. Can we conclude that x and y are indeed linearly related with some level of confidence? And then determine the equation for the regression line that best fits the data. So you're just given your data points. How do you go about solving this problem? Well, looking back at our formulas, we have all these sums of things, sums of the x values, sums of the y values, sums of the squares of the x's, sums of the squares of the y's. We have all these things going on here. So let's just actually get what each of these things are first, and then once we have those numbers, we can just substitute them into this formula. So what I suggest you do is I suggest you create a table like such. Take every ordered pair, label the x and y coordinate, as I did here, 1, 3, 2, 5, 3, 9, and 4, 6. And now we have x squareds, we have y squareds, and then we have the product of the x and the y value. So find each of those things. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 3 squared is 9, 5 squared is 25, 9 squared is 81, and 6 squared is 36. And then take the product of the x and the y values. 1 times 3, 2 times 5, 3 times 9, and 4 times 6. Add all these things up, and you get those sigmas. You get those sums of the x, sum of y, sum of x squared, sum of y squared, so on and so forth. All those things that we're going to need to substitute into our formulas. The other thing we needed was n. N was the number of ordered pairs that we had, or the number of data points. That was 4. So n is equal to 4. We now have the 6 pieces of information that we need to substitute into our formulas here. So when you take those 6 values and substitute them into the formula for the correlation coefficient here, you're going to get n was 4. The sum of the product of x and y was 64, minus sum of the x's was 10, sum of the y's was 23. On the bottom, the square root of, it was n times the sum of x squared, that was 30, minus the sum of the x's, which was 10, that number squared, times n times the sum of your y squareds, which was 151, minus the sum of your y's, which was 23, that number squared. When you multiply these things out and at least make it a little bit nicer, 4 times 64 is 256, 10 times 23 is 230. That's going to leave you, when you take the difference, of 26 on the top. 40 times 30 is 120, 10 squared is 100, 120 minus 100 is 20. And then this calculation right here, I'll let you verify on your own that you get 75. So you have 20 times 75, which is 1500. So we have the square root of 1500 on the bottom there. The square root of 1500 is approximately 38.72893. And if you do 26 divided by that number, you get approximately 0.671317. There is a little bit of room that you can have here for a slightly different answer, but it should be really darn close to 6.71 or somewhere pretty darn close to that. You should only be off by about maybe a couple thousandths or so. So this was our correlation coefficient, an R value of 0.67. It does suggest that there is a fairly strong linear relationship between the two. But as we saw in our previous video, based on the number of data points that we are using, we have to see if this R value is greater than or equal to some particular values, and if it's greater than or equal to at least one of them, then we have a reasonable confidence in the assumption that these two quantities, x and y, would indeed be linearly related. So taking a look at that chart once again, it's all based on our sample size. Well, we had 4 data points, so n is 4 here. So if our R value is greater than or equal to 0.95 or 0.99, then we have reasonable confidence that those two data sets are linearly related. Our R value was 0.67, so we're not quite there. We're not quite at 0.95 or 0.99. So we don't have a lot of confidence that these two quantities, x and y, whatever they are indeed linearly related, but still 0.67 is not that bad. So for the sake of continuing on with the problem, we will operate under the assumption that these two indeed are. Just to clarify, this table right here, if your R value is greater than or the same as any one of these two numbers in the 5% significance or the 1% significance columns, then you are like really sure, there should be almost no doubt in your mind that these things are indeed linearly related. If you have an R value that's less than something in the 5%, then that doesn't necessarily mean that the two quantities aren't linearly related. This just is a way to tell if you can be very sure that the two are. All right, so let's continue on. Let's find the A and B values, or the slope and the y intercept for our line of best fit, or our regression line. As a recap, the formulas for the slope B and the y-intercept A in a plus bx are given right here. So we are going to do those calculations. We're going to figure out what those things are. So b value was n times the sum of the product of x and y, 4 times 64, minus the sum of the x's, which is 10, times the sum of the y's, which is 23. And that's all over our n value, times the sum of the x squareds, 30, minus the sum of the x's, which was 10 squared. And we did this, we did these calculations up here when we found r. So we can just copy those numbers over. We get 26 over 20, or 13 over 10. Now, typically, you do want to start to get into the habit of writing things in a fractional form, but when it comes to writing lines of best fit, you do typically see these things written in a decimal format. So 13 over 10, or 1.3, that's perfectly fine. Once you have your b value, you can now find your a value, because looking back at the formulas, you see here that you need your b value to calculate your a value. So the a value is the sum of your y's, which is 23, minus your b value times the sum of your x's, which was 10. And that's all divided by n, which was 4. So 1.3 times 10 is 13, 23 minus 13 is 10, and 10 over 4 is 5 halves. So we have our a and b value, and we write the equation for our regression line. 5 halves is 2.5, so our line is y equals 2.5 plus 1.3x. And this is the line of best fit for our given data points for this particular problem. So as you can see, clearly there was a decent amount of work that had to be done in here. Some of the calculations, like finding that correlation coefficient R, that was kind of nasty, but creating this table here and labeling what are the pieces of information that you need. What's the sum of your x's, the sum of your y's, sum of your x squareds, and all that stuff. You know, having that all taken care of beforehand, that does make things significantly easier when you do all these calculations. So let's go right into our next problem. You're going to do the exact same thing, but you're going to do it with 5 data points this time. You're going to do it with 1, 2, 2, 4, 3, 3, 5, 7, and 6, 7. So what I want to sort of challenge you to do is to first just come up with that table like we did for our previous sample problem here. You know, write the x and the y coordinates of each of your points. Write the x squareds, write the y squareds, write the product xy, and then sum each of those things up and come up with these 6 values that you need to substitute into those nasty looking formulas that we have there and make things a bit easier on ourselves. So pause the video here, do those calculations, then once you think you have them, press play, and we'll see if you were correct so far. All right, so let's see if you got your table correct thus far. So this is what you should have here. N was the number of data points that we had. We were given 5 ordered pairs, so that is our n value. You see here I wrote the x and y coordinates for each of our 5 points, squared the x's, squared the y's, took the product of the x and the y values, and then I added every column. Sum of my x's was 17, sum of my y's was 23, sum of the squares of the x's was 75, sum of the squares of the y's was 127, and sum of the product of x and y, sum of this column here was 96. So hopefully you got those values right. Now, once again, I will challenge you to calculate your correlation coefficient R. Plug all these values into the appropriate formula here and see what you come up with as your R value. And then once you have found your R value, then use your table to figure out whether the two quantities x and y, whether we have that significant enough confidence that the two quantities are indeed linearly related. So once again, press pause here, do that calculation, and arrive at that conclusion based on your calculation. And once you have it, press play and we'll see if you are correct thus far. All right, guys, let's see if you got the correct correlation coefficient. Again, it is n times the sum of the product of x and y. So 5 times 96 minus the sum of the x's times the sum of your y's. So 17 times 23. On the bottom, you have the square root of n times the sum of the squares of the x's, 5 times 75, minus the sum of the x's, 17 squared. That number times this quantity, n times the sum of your y squareds. So 5 times 127 minus the sum of the y's, 23 squared. When you multiply on top and then you take the difference, you get 89. This calculation right here, again using those or that order of operations, you get 86 for this guy right here. This guy right here, you get 106. If you do the product, 86 and 106, you then take the square root of that number and you do 89 divided by that quantity. You should get approximately 0.93215. So looking at this R value and looking at our table here, again, we need our sample size, our n value. Our n value was 5. So as long as our correlation coefficient R is greater than either one of these two numbers, looking at the row where n is equal to 5, then we are very confident that these two quantities are indeed linearly related. And as it turns out, our R value of 0.93 is greater than the 0.878. Not as large as the 0.959, but it is larger than this guy. So yes, we can be very confident that these two quantities, x and y, whatever they are indeed linearly related to each other. So now that we know that these two quantities are indeed truly linearly related to each other, we can now find our A and B values that will make up the missing pieces, if you will, of our regression line or our line of best fit. So once again, I'll challenge you, finish off this problem on your own, do the calculations, figure out your A and your B values, and once you think you have those, plug them into this guy right here. So press pause, solve the rest of the problem on your own. Once you think you have the answer, press play, and we'll see if you were right. Okay, let's see if you came up with the correct A and B values. So B here, again, n times the sum of the product of the x's and y's minus the product of the sum of the x's and the sum of your y's. And then n times the sum of your x squareds minus the sum of your x's squared. Do these calculations, again, using order of operations. On the top, you get 89. On the bottom, you get 86. Converted to a decimal, you get approximately 1.0349. Based on how many places you round to, if you rounded to 3, you get 1.035, but basically somewhere close to 1.03, and you're good. Now the A value here, it's the sum of your y's minus your B value times the sum of your x's, which was 17, all divided by our n value of 5. Use your order of operations, do this calculation, and you get 1.0813 approximately. So then we can thus say that the regression line has equation y equals 1.0813 plus 1.0349x. And this is the equation for the regression line, or the line of best fit, for our given 5 ordered pairs here. So guys, these are the 2 sample problems I wanted to go through on this topic. Yes, I know they're not pretty. They're not the easiest type of thing to do. However, what we do here and what we talked about in this video, as well as our previous video, is very, very important in the real world. A lot of scientific studies, a lot of testing of theories and testing of relationships between 2 ideas or 2 quantities. A lot of testing that's done with those things is doing this kind of thing right here, coming up with a linear regression model between these 2 quantities, whatever they may be. And in your homework, you will see many sample cases where we use this technique and where we use all of these calculations. So this is a big thing out there in the real world. So it definitely helps to know what is going on here when they talk about this method and what they're doing. So that concludes our video on this topic. Guys, if you have any questions or comments, please be sure to reach out to me. Send me emails, send me texts, send me postcards. Drop a bomb on my house letting me know that you need help, whatever you have to do. Otherwise, until the next video, take it easy, guys.